This video is about equations of planes. So we're in the context of 3 dimensions, right? So we have planes in 3-dimensional space. How do we describe a plane in 3-dimensional space? Well, intuitively, a plane is something that's flat. So it's going to be something like this, and it's going out in infinite direction, right? So it's going out forever, and the question is, how do we find an equation for the plane? In other words, so what does it mean to find an equation for a plane? We're looking for an equation involving x, y, and z. Here's the positive x direction, positive y, positive z. We're looking for an equation involving x, y, and z such that when you look at all the points x, y, z that satisfy the equation, okay, that's going to be a subset of R3, the points that satisfy this equation, that you end up getting the plane. That's what we're looking for when we say that we're looking for an equation for the plane. Well, suppose that you have a point suppose that you have a vector that's perpendicular to the plane, like this. So let's call this vector n. Perpendicular to the plane means that when you have 2 points on the plane, so let's call this point P0, and let's call that point P. If you have 2 points on the plane and you take the difference, P minus P0, okay, that you get a 90-degree angle with the vector n. So that's supposed to be a 90-degree angle. Okay, that's maybe not looking like a 90-degree angle, so maybe n looks more like, see, but this is in perspective, right? So maybe it looks more like this. So you get a 90-degree angle like this. So let's say that P0 is x0, y0, z0. And you have a vector that's perpendicular to the plane, then no matter what point P you have, so let's make a different point P, okay, whatever, x, y, z, right, your x, y, z here and x, y, z there, if you take the vector, whatever your x, y, z is, if you're on the plane, if you take the vector from P0 to P, the vector n should be perpendicular to all the vectors from P0 to P. So let's say that our vector n is a, b, c. Let's say those are the components. Then P minus P0, so let's just clarify that we're taking the vector OP and OP0. So here's OP. And OP0 is this vector. Okay, so this is OP, OP0. If you take OP minus OP0, okay, you get this vector. This vector should be orthogonal to n. If P is on the plane, then OP minus OP0 should be orthogonal to n. So what that means in terms of the dot product, well, what does that mean in terms of the dot product? The dot product is 0, right? You're going to get n dot, this vector OP minus OP0 is going to be 0. And if we use the coordinates, so n is ABC, OP is XYZ. OP naught is the vector x naught, y naught, z naught. This should be 0. This ends up, when you distribute, well, actually we can simplify what's in the parentheses first. X minus x naught, y minus y naught, z minus z naught. This dot product should be 0. What's the dot product? Well, you just multiply the components and add them together. So it's a times x minus x naught plus b times y minus y naught plus c times z minus z naught should be 0. And we can distribute this even more because you're going to get ax minus ax naught plus by minus by naught plus cz minus cz naught equals 0. We just get that by distributing, and then we can add these terms ax naught, by naught, cz naught to the other side, and that gives us ax plus by plus cz equals ax naught plus by naught plus cz naught. And that's an equation of the plane. So if you're given a point x naught, y naught, z naught on the plane, and you're given a normal vector ABC, then a point xyz is on the plane precisely when it satisfies this equation. So just maybe to emphasize, this is called a normal vector to the plane. That's what the n stands for, normal vector. Normal is the same as perpendicular. It's just a synonym, another word for perpendicular. Okay, so one plane will have a normal vector and a different plane is going to have a different normal vector. So it's not just a normal vector, period. It's a normal vector to a specific plane. Put this in the box. And this has the form, so the A, B, and C, and x naught, y naught, c naught, z naught are constants. So this has the form ax plus by plus cz equals d for a constant d. And it turns out that for any constant d, and A, and B, and C, that this defines an equation of a plane. So that has the form ax plus by plus cz equals d for constants A, B, C, and D. And then conversely, any equation of the form ax plus by plus cz equals d for constants a, b, c, and d gives rise to, is the equation of a plane. Okay, why is that true? Because let's see. Maybe we can just give a specific example. So for instance, let's say that you had x plus 2y plus 3z equals 5. What's the graph of this equation? Well, suppose that I had 2 points x, y, z that satisfy this equation. So if I have something like, oh, actually for simplicity, let's just make the 5 into a 6, just to make the numbers work out better. So you could have something like 6, 0, 0, that's on the plane, right? Or you can have 0, 3, 0 is on the plane. These are on the plane because so these points are on the plane because they satisfy the equation, right? They satisfy the equation. So they satisfy the equation, which means they're on the plane. And so I have these points, let's call this P and let's call this Q. So I have this point P and this point Q. And notice that if you subtract QP, so you take the vector from from Q to P, this is going to be negative 6, 3, 0. And this vector is perpendicular to the vector 1, 2, 3. This is orthogonal to the vector 1, 2, 3. Notice that the 1, 2, and 3 are gotten as the coefficients of x, y, and z. That leads to this vector. And in general, if you take any p, so let's say you replace p by x, y, and z, so you have x, y, z, then qp, so let's just work with the specific q, 0, 3, 0. Qp is x, comma, y minus 3, comma, z. This is orthogonal to the vector 1, 2, 3. Because 1, 2, 3 dotted with x, y minus 3z is equal to x plus 2y minus 6 plus 3z. And we know that x plus 2y plus 3z equals 6, and so this is going to be 0. If you take any point P on the plane, right? Q and P are points on the plane. And if you have, so what did we show? We showed that if you have this equation and you look at the set of points that satisfy this equation, it's precisely the set of points x, y, z such that that point, that vector minus OQ is perpendicular to 1, 2, 3. So what the graph of this looks like is you have this point 0, 3, 0. That's like this point. So this is Q. It's all the vectors, it's all the points P such that QP is orthogonal to 1, 2, 3. So 1, 2, 3, I don't know, is like this, say. And you want all the points P such that QP is orthogonal to 1, 2, 3. So if you take all the points, you're going to get a plane like this. So that's what the plane is going to look like. So that's how you know that this is the equation of a plane. You can do the same thing. See, here I worked with a specific example where A, B, C, and D were 1, 2, 3, and 6, but it works in general. So that explains why ax plus by plus cz equals d is the equation of a plane. And we know that a normal vector is going to be a, b, c. Now don't get too hung up on the a, b, and c. because notice that if you have something like an equation of a line, we had something like R of t equals a plus x0 t, b plus y0 t, c plus z naught t, or no, sorry, you want a point on the plane, on the line, and then a direction vector. So if your direction vector is ABC, then it's going to be x naught plus AT, y naught plus BT, z naught plus CT. And if you have an equation of a plane, it's a x minus x naught plus b y minus y naught plus c z minus z naught equals d. And one of the things that I think students find confusing is they look at the symbols. They look at the symbols and say this looks like this because there's x naught, y naught, and z naught, and there's a, b, and c. But these are very different things. So when I look at this, okay, what's telling me that I have a line? So first of all, I see, this is the function notation, I see that it's taking t as an input. Okay, it's taking one input, a real number as an input, and it's producing this vector with 3 components. So when I see something like this, I know that I'm going to get a curve in 3-dimensional space. And what's telling me that I have a line specifically is that if I write this as x naught, y naught, z naught plus t, a, b, c, this has the equation of a line. Okay. So what I think of when I see this is I have a point x naught, y naught, z naught, and then a direction vector a, b, c, and then I get a line like this that just goes out forever. So that's what I'm looking at that tells me that this is an equation of a line. When I have something like this is something that's completely different. It's not a parametric equation. And this A, B, C is really not the same as the A, B, and C. Like these A, B, C's are really not related. Like these are unrelated. These are unrelated. They have nothing to do with each other. So don't just look at the equation, like the symbols, the letters, and be like, well, these letters are the same as these letters, so they're the same. But they're completely different things. Okay, the first thing is the equation of a line. My ABC is a direction vector. It's a vector that's parallel to the line. Remember, that's what a direction vector is. So direction vector to a line. And then for a plane, when I have this, okay, this on the right, this is the picture that I have in my head is I have this vector ABC like this. And then I have a point x naught, y naught, z naught that's on the plane that, say x naught, y naught, z naught is here. And then it's saying that when I take a point x, y, z, and then take the vector, not d, this should be 0, right? Because I get the d by adding the term to the right. So when I have something like this, it's saying that when I take the vector from here to here, I get a 90-degree angle. This is perpendicular. Okay, so maybe I'll just make my vector look more perpendicular. So I get something like this, and then when I take all the x, y's, and z's, I get this plane that's perpendicular to the vector ABC. Okay. And if I rewrite this equation as ax plus by plus cz equals d, then again, I have the same thing. Okay, we're not given a point. When you write the equation in this form, you're not given a point on the plane, but it's easy to come up with points on the plane. You just come up with x, y, and z that satisfies the equation. And I still see an ABC, so, and this is saying, since I know that this equation can be rearranged to give this equation, I recognize that this is an equation of a plane with a normal vector ABC. So this is a plane with normal vector ABC. So completely different pictures, okay? Completely different things. Because this is actually like a function. I mean, this is a function where when you plug in all the values of t, you get this line as the output. This is an equation where if you look at all the x, y's, and z's that satisfy this equation, or that equation, you get this plane. So don't think that they are somehow related. Okay, you should think of these as completely separate things and not get hung up with the letters. So for instance, if I had, 2x plus 3y minus z equals 5, when you look at that, you immediately think of it's a plane. And by the way, you can also rearrange this. If I add z to both sides and then subtract 5, this is going to be z equals 2x plus 3y minus 5. And one way I can think about this in terms of functions is I can think of z as a function of x and y. So I could think of f of xy equals 2x plus 3y minus 5. And the plane, which consists of all x, y, and z that satisfy the equation 2x plus 3y minus z equals 5, this is the graph of the function f of xy equals 2x plus 3y minus 5. So now I have a function of two variables. So I have, if you think of the xy plane as the domain, maybe I won't draw this. The xy plane as the domain of this function, and I use the z-axis to plot the graph of this function. So if I take a point x comma y, I guess well, technically I'm in R3, so I guess comma 0, then the point above it on the graph is going to be this point x comma y comma 2x plus 3y minus 5. If I do that for all the points, I'm going to get this this plane. And I see that I have a normal vector 2, 3, negative 5. No, sorry. What am I saying? I have a normal vector 2, 3, negative 1, right? So let's just plot a point. Let's say you plug in, I don't know, 1 comma 2. So if you plug in 1 comma 2, you're going to get 2 plus 6 minus 5 is 3. So you get this point 1, 2, 3, like this. Maybe it's a bit higher. So this is a point on the plane that's above the point 1, 2, 0. And then I should call this 1, 2, 0. And then you have this normal vector 2, 3, negative 1. So that's a normal vector, right? 2, 3, negative 1. That's maybe like this. And then I have all the points such that when you take the difference between this point and 1, 2, 3, so if I take a point like here and I look at this vector, it looks like it's perpendicular to this vector, this normal vector. And then if you take all the points with that property, you're going to get a plane like this. So that's a sketch of this plane. Right. I'm thinking of this as the graph of this function f of xy. If you plug in all the xy points on the xy plane into this function and graph, you plot all the points you get, you're going to get this plane. Okay, so let's do some examples. Find an equation of the plane that contains P, which is 1, negative 2, 0, Q, which is 3, 1, 4, and R, which is 0, negative 1, 2. So let me draw my little generic picture. Here's P, Q, and R. I have these 3 points. And I'm trying to find a plane, the equation of the plane that contains these 3 points. So what I need to find the equation of the plane is I need a vector that's perpendicular to the plane. That's what we call the normal vector to the plane. And we need a point on the plane. Well, here we have 3 points on the plane. What's missing is the normal vector. So what we can do to produce the normal vector to the plane is when you have 2 points on the plane, remember the normal vector is orthogonal to that difference. If you take these 2 points on the plane P and Q and take the vector from P to Q, the normal vector is going to be orthogonal to this vector. And if I take, say, the vector from P to R, the normal vector is going to be orthogonal to that. So the normal vector, so what we have is we have a point on the plane. We actually have 3 points on the plane, but we have 1 point on the plane. And what we need is a normal vector to the plane. Because once we have a normal vector to the plane, we can use the equation for the plane that we went over. And the normal vector, let's call it n. We know that n is orthogonal to both PQ and PR. How can we find a vector that's orthogonal to PQ and PR? If you have 2 vectors, what can you do? You can take the cross product, right? So in this case, PQ is, okay, you take the coordinates of Q and subtract the coordinates of P. So you get 2, 3, 4. So we have PQ and we have PR is negative 1, 1, 2, right? So we can take n to be the cross product PQ cross PR. Notice that you just need one vector that's orthogonal to PQ and PR. Okay, n is just any vector that's orthogonal to the plane. So like this could be your n, that could be your n, this could, well, we want it to be orthogonal. Yeah, I have a hard time drawing vectors that look perpendicular to the plane. So maybe I should, oh, how do I draw something that looks perpendicular to the plane? Does that look perpendicular to the plane? Sure. let's say that's perpendicular to the plane. We can take any non-zero scalar multiple of a vector that's perpendicular to the plane and use that as our normal vector n. Okay. You just need one vector perpendicular to the plane. Okay. There isn't a specific, it's not like there's only one possible n that works. You just need one vector that's orthogonal to PQ and PR, so why not just take the cross product? Because we know that's orthogonal to PQ and PR. So what's the cross product? PQ cross PR is can we do this in our head? The I coordinate is 6 minus 4, which is 2, and then minus j, which is 4 minus negative 4, which is 8, and then plus k. 2 minus negative 3 is 5. So we get the vector 2, negative 8, 5. And by the way, don't hesitate to write out more steps to make sure that the algebra is correct, because it's kind of tricky with the minus signs. But anyway, this is correct, so we can make that our n. Okay, that's our n. And we have a point. And we can use any point we want that's on the plane. So why not just use p, 1, negative 2, 0. So the equation of the plane that we want is 2, 8, 5 dot x minus. So again, we can use our p as our x naught, y naught, z naught. So x minus x naught is 1, x minus 1, comma, y minus negative 2, that's y plus 2, comma, z minus 0 is z. So you get this dot product is 0, right? That's what should happen. Because this vector should be orthogonal. This vector should be orthogonal to the normal vector. And now we shouldn't leave it like this, we should distribute. So you get 2 times x minus 1 plus 8 times y plus 2 plus 5z equals 0. Or alternatively, if you just remember the formula, if you just remember this formula, you can use that directly. You didn't have to write out the dot product. But, okay. So that's an equation of the plane. But it's more standard, just like when you have the, what is it called for the line? The point slope form. That's not very standard, right? Because if you have a different point, you're going to get a different equation. So it's more standard to write it in the form y equals mx plus b. In the same way, it's more standard to write an equation of plane in the form ax plus by plus cz equals d. So let's write it like that. So you're going to get 2x minus 2 plus 8y plus 16 plus 5z equals 0. So that's 2x plus 8y plus 5z equals, add 2 and subtract 16, so you get negative 14. Did I do that right? Oh, no, because there's a minus sign here. Okay, so there's a minus sign here. So it's actually minus 8y minus 16. So this is going to be 2x minus 8y plus 5z equals 18. Okay. And then maybe one more kind of, okay, so we're done with that problem. And then one more thing I'll say is that just to make sure we're okay on the different things that's going on. So when you have a line in 2D, it's often written as y equals mx plus b. And then the analog, so this is in 3D, you're going to have z equals something, right? Like z equals, I don't know what letters to use, kx plus ly plus m or something. That would be the analog. That would give you a plane in 3D. Or if you have the standard form, ax plus by equals c, for a line in 2D, in 3D, that has a more simple analog, right? So that's what we're doing for a plane. And then if you have the form that's y minus y naught is m times x minus x naught, for a plane, the analog is, see, like this would correspond to mx minus x naught minus y naught equals 0. Then that would correspond to a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So I hope that makes it clearer how these things match up. I mean, I guess you could have something like a times x minus x naught plus b times y minus y naught equals c if you rearrange things. Equals 0, sorry. So let's see, in 2 dimensions, if you have a line, let's go back to the equation 2x plus 1. So 2x plus 1's maybe like this. What would that look like in terms of our, like the analog of the equation of the plane that we found with the dot product? Then it would be like if you have a point 0, 1, and you have another point which is 1, 3. This vector, this would be like your p naught, and then this would be like your p, and then the difference, p naught p, would be 1, 2. Right? So you would have this vector 1, 2. And then you would want a normal vector. Normal vector is perpendicular to this line. And then your n would be negative 2, 1. So your equation would be like, the equation of the line would be like n dotted with this vector p naught p is equal to 0, which would mean that if you have the point p, which is, okay, instead of 1, 3, you just replaced it by x, y. Then you have p naught p is x, y minus 1. And this equation would be negative 2, 1 dot x, y minus 1 is 0. That's negative 2x plus y minus 1 is equal to 0. Plus 1 times y minus 1 is 0. It's this equation. So this would be, this equation of the line that we wrote is analogous to this equation for the plane. Okay. So that's basically a quick overview of equations of planes. They're analogous, a lot of it is analogous to equations of lines. So let's just review what we did. We discussed how to find an equation of a plane in three-dimensional space if you have a normal vector to the plane and the point on the plane. You can describe the points on the plane either by this equation or the equation below it. And we got that because we have this equation, the dot product. I use this hat for the normalized unit vector, normal vector. So if you have n dot p naught p, you should get 0. That's the key thing. And when you just kind of write it out in terms of coordinates, you get this equation for the plane. And whenever you have something of the form ax plus by plus cz equals d, the set of points x, y, z that satisfies it is going to be a plane. And we did an example of this. And we did some comparisons between the equations of a line and equations of the plane, because I think a lot of students will look at these two and just kind of mix them up because they're focusing on the letters. And what I'm trying to say is you shouldn't focus on the letters. You should focus on what these equations are telling you. And once you think about that, you'll see that you get completely different things. One is a line and one is a plane. This ABC for the R of t on the left, the ABC is a direction vector. Direction vector is a vector that's parallel to a line, right? A direction vector of a line. So this line has a certain direction vector. Different lines can have a different direction vector. Parallel. For a plane, different planes are going to have different normal vectors. Normal vectors are perpendicular to a plane. And we saw how when you have an equation of a plane, you can think of the plane as the graph of a function of two variables. And we did an example of this. We did an example of a problem of finding an equation of a plane that contains 3 points. Okay, you just take PQ and PR and take the cross product. That gives you a normal vector, and then you can use any point on the plane to find the equation of the plane. And by the way, it didn't have to be PQ and PR. You could have done QP cross QR. So you could have done, if you had QP and QR, right, and then did the cross product, you would also get a vector that's perpendicular to the plane. Okay. And at the end, we just did some comparisons, a few more comparisons that show you how the equations of lines are analogous to the equations of planes. And I think that's helpful for understanding how the different concepts are related. And I did an example of how to get this dot product interpretation, right? We use the dot product to find the equation of a plane. We could do the same thing for a line. If you have a line, you take a point on the line. So in this case, we take 0, 1. And then if you take any point P on the line, call it x, y, then the dot product of the normal vector with the vector P naught P is going to be 0. And then when you write it out, you get this. So this equation is analogous to this equation. Right? This is like this equation that we found at the end. This is like the 2D analog of the equation of a plane.